Welcome to this video. In this video, we are going to discuss about square wave generator using operational amplifiers. Square wave outputs are usually generated using an op-amp when it is forced to operate in the saturated region. That is, we can generate square waves when we force the op-amp to operate in the saturated region. That is, the output of the op-amp is forced to swing repetitively between positive saturation plus Vset, which is approximately equal to plus Vcc, and negative saturation minus Vset, which is approximately equal to minus Vee. So we will get a square wave by swinging the output between plus Vcc and minus Vee, or plus Vset or plus Vset and minus Vset. Plus Vset means saturation, positive saturation, and minus Vset means negative saturation. The circuit for such a square wave generator is shown in the figure. In the left side figure, we can see a square wave generator using op-amp. It is also known as a free running or a stable multi-vibrator. In this particular circuit, the output of the op-amp can be positive or negative saturation depending on the differential voltage VID, which is negative or positive depending on the polarity of the differential voltage VID. VID is V1 minus V2. Depending on the polarity of the differential voltage VID, the output of the op-amp can be positive saturation or negative saturation, and we will get a square wave output. Now we can see how it works. First of all, assume that the voltage across the capacitor is 0 volts at the instant the DC supply voltages plus Vcc and minus Vee are applied. That is, suppose let us assume that the voltage across the capacitor C in the feedback path, we can assume that the voltage across that capacitor is 0 at the moment the DC supply voltages plus Vcc and minus Vee are applied. This means that the voltage at the inverting terminal is 0. That is, the voltage at the capacitor appears at the inverting terminal. So we can say that the voltage at the inverting terminal is 0 since the voltage across the capacitor is 0 initially. At the same instant, the voltage V1 at the non-inverting terminal is a very small finite value, which is a function of the output offset voltage VOOT and the values of resistors R1 and R2. We know that in practical cases, the two terminals of the op-amp are not identical. So, a small voltage will produce an output. We can say that voltage as output offset voltage. So the voltage at the non-inverting terminal V1 can be a small finite value, which is a function of output offset voltage and the values of resistors R1 and R2. Thus, the differential input voltage VID is equal to the voltage V1 at the non-inverting terminal, because VID equal to V1 minus V2, V2 equal to 0, but V1 is a finite, a positive quantity. So, the input voltage VID is equal to V1. Even though this particular voltage V1 is very small, it can start to drive the op-amp into saturation. For example, suppose that the output offset voltage VOOT is positive. Therefore, the voltage V1 is also positive. Since initially the capacitor, the voltage across the capacitor is 0, the gain of the gain of the op-amp is very large. Hence, V1 drives the output of the op-amp to its positive saturation plus Vset. Initially, we assumed that the output offset voltage is a finite small positive quantity. So V1 is also a positive quantity. So the differential input voltage V1 minus V2, because V2 is actually we have chosen V2 equal to 0. So the differential input voltage V1 minus V2 is equal to V1. It is a positive quantity, and since the voltage gain of the op amp is very high, V1 drives the output of the op amp to positive saturation. Since input is positive, output is also positive. Hence, V1 drives the output of the op amp to its positive saturation plus Vset. When the output voltage of the op amp is at plus V saturation, the capacitor C starts charging towards plus V saturation through resistor R. The capacitor is connected in the feedback inverting to input terminal. So when the output voltage is plus Vset, the capacitor will start to charge towards plus Vset through the resistor R. But when the voltage V2 across the capacitor C is slightly more positive than V1, the input becomes V1 minus V2 becomes a negative quantity, and hence the op amp is forced to switch to a negative saturation minus Vset. That is, when the capacitor is charged to a positive voltage, the differential voltage VID becomes V1 minus V2 becomes a negative quantity. Since the input is negative, the output will be forced to negative saturation, that is minus Vset. We can say that or we can write the voltage V1 across R1 when the output voltage is forced to minus V saturation, the voltage V1 across R1 also becomes negative. The voltage V1 across R1 can be written as V1 equal to R1 V1 equal to R1 by R1 plus R2 into minus V saturation. Thus the net differential voltage VID is V1 minus VID equal to V1 minus V1 minus V2 is negative, which holds the output of the op amp in negative saturation. And the output remains in negative saturation until the capacitor C discharges and then charges to a negative voltage slightly higher than minus V1. So when the output voltage becomes negative saturation, the capacitor begins to discharge. When the capacitor completes discharge and then recharges to a negative voltage slightly higher than minus V1, the input differential voltage VID equal to V1 minus V2 becomes slightly positive, and hence the output of the op amp is driven to plus Vset. This completes one cycle. That is, when the output voltage becomes minus Vset, the capacitor starts discharging, and after completing discharge, it begins to charge towards minus V saturation. When the voltage, so V2 equal to the capacitor across the voltage which is negative polarity. So the differential voltage VID equal to V1 minus V2 becomes slightly positive, and again the voltage goes to positive saturation. This is the one cycle. This completes one cycle. With the output at plus V saturation, the voltage V1 at the non-inverting input is V1 equal to R1 by R1 plus R2 into plus V saturation. The time period T of the output waveform is given by T equal to 2RC log 2R1 plus R2 divided by R2. By taking the reciprocal, we can find the frequency of the output. These are all input square wave generator.